بسم الله الرحمن الرحيم. الحمد لله رب العالمين، والصلاة والسلام على الحبيب المصطفى صلى الله عليه وعلى آله وصحبه أجمعين. أرحب بكم في هذه الورشة ضمن سلسلة مهندس عن بعد. محدثكم الدكتور عبد الرحمن بن إبراهيم القاسم، عميد كلية الهندسة بالجامعة الإسلامية بالمدينة المنورة، والأستاذ المشارك بقسم الهندسة الكهربائية بالجامعة الإسلامية. سنتحدث اليوم عن قضايا متعلقة بإدارة الطاقة في جانب المستهلكين Demand Side Issues in Energy. So the outline includes talking about the supply side resources and demand side resources, then the impact of demand side management, the concept and the challenges for its implementation. Then we'll look at some examples of savings in demand side management and its cost effectiveness. Then we will finalize by looking at the promise versus the reality of demand side management. So what is the demand side? It's basically the part of energy system that involves the consumption and end use of energy. Anything in the load side or the consumption side or behind the meter side can be considered in the demand side. The stakeholders or key players in this concept are the consumers with their different classifications: residential, commercial, industrial, besides the utilities and the policy makers. The importance of addressing the demand side management comes from the need to balance the supply and demand, to reduce the peak loads and accordingly reduce the stress on the grid, in which we can look at the power consumption, not only the energy consumption, not the cumulative consumption, but what time is it used. The enhancement of energy efficiency and conservation, two important terms have to be distinguished from each other. Then lowering energy cost for consumers and promoting sustainable energy practices. While we will also look at the challenges in the demand side management, including the insufficient energy consumption, which is related to the energy efficiency improvement, the peak demand challenges related to the demand side management, then the lack of consumer awareness and behavioral barriers. So if we look into the energy pyramid, in the left side, it shows the three main phases of energy pyramid, starting at the bottom with the energy conservation. Basic measures usually come with a comparatively lower initial cost and have somehow limited impact in comparison to the other parts in the energy pyramid. So energy conservation, something like installing an insulation system, reducing the number of lights used, so either through some installations or through behavioral change. Then we have energy efficiency. In energy efficiency, the difference is that we are seeking to get the same output, the same final output, while the input is reduced. How? Because the energy efficiency requires, or the energy efficiency results in a lower demand of the resource, of the input, to get the same result as an output. Then at the top of the pyramid, we have the renewable energy. If we look into the right side, we have a more comprehensive version of the energy pyramid that starts at the bottom with the energy analysis, which is a mandatory step to define what are the heavy energy users, what type of uses there are. Usually we use different auditing levels through parameters like energy cost index, energy use index, to find out how the system is working and where the improvements can reside. Then coming back again, energy conservation, energy efficiency, then the time of use management, which is the focus mainly of our work, and at the top of our workshop today, then at the top of the pyramid is the renewable energy. So pioneering initiatives led by the Ministry of Energy in this area include the optimal energy mix, the National Renewable Energy Program, Saudi Energy Efficiency Center, and the Liquid Fuel Displacement Program. We'll focus on the Saudi Energy Efficiency Center, which aims to rationalize the increase of efficiency consumption in the main three sectors: the residential, the industrial, and transportation. Then we have the optimal energy mix, in which under the Saudi 2030 vision, there is a target to achieve 50% renewable energy in the energy combination or the energy mix. So the diversification to play a complementary role for the renewable energy to play a complementary role with conventional energy sources is one of the important initiatives. Looking at the beginning at the energy efficiency center objectives, it includes, as we can see, number one, تحسين كفاءة إنتاج الطاقة, so at the generation side, and in number two, تحسين كفاءة استهلاك الطاقة, so improving the efficiency both in the generation side and in the consumption side, among their other objectives. Looking at the renewable energy, we can see the snapshot of the worldwide cumulative capacity, which is gradually increasing, and it reached about 3.8 terawatt by 2023. We can also see here the net addition per year. So we can see again that 2023 witnessed more than 450 gigawatt of installation from mainly solar PV, among others, hydropower, wind, and bioenergy. So basically the idea is, with increasing the share of renewable energy sources in grids, comes the importance of demand side management, because it is hard to control the generation side with more portion of the grid coming from renewable energy in comparison to how we can control it when it's conventional energy sources. Why? Basically because we don't have as much control on the resource, on the fuel of our generation. So looking into the Saudi context in renewable energy, we can see here that 58 gigawatt is intended to be installed by 2030, which increases the portion of renewable energy, as we said, to 50% from the energy mix. So the energy diversification between conventional and renewable energy is the target. Looking at the supply side resources in comparison or in the context of the classification of the load, base load, intermediate, peaking, we can see these are the conventional resources in the base that cover the base load, the combined cycle with cogeneration, coal. Then we have some of the renewable that provide somehow constant power delivery, like run of river hydro, geothermal. In the mid-range, to cover the intermediate load, again, we have the combined cycle. For peaking, we have gas turbines, we have peaking hydro, and then we have some terms like exchanges, where peaking capacity with off-peak energy return, so on-peak and off-peak, seasonal capacity exchanges, which can happen within a certain location or from one country to another, neighboring countries that have interconnection of their grids. The renewable, solar, wind, hydro, photovoltaic, solar, thermal, biomass, geothermal, can cover different classifications of these loads. Also, they can be supported by energy storage, like pumped storage, compressed air, fuel cells, batteries. Of course, those have their own challenges, especially when we talk about it at a utility scale. That's in the supply side. Let's look at the demand side resources. There are programs that are designed to modify the demand through either energy efficiency improvement. So as we said, you replace or you install appliances that have higher efficiency. They deliver same output with lower input, or through energy conservation in terms in which the input is reduced. Then we have electricity consumption reduction, strategic reduction, or we can try to find ways to shift the loads to periods with lower demand. That can be looked at the medium term, the long term, with more integration of renewable energy sources, but it has its own challenges that have to be considered and looked at solutions, opportunities to make them effective. We refer to such programs as demand-side management or demand-side resources. So as a matter of fact, demand-side resources doesn't refer to a real resource. Rather, it's metaphoric. So conceptually, we may view the demand-side management as a source of energy for meeting the system demand. Why? Because we have the generation side, we have the demand side. We can increase the generation side or reduce the demand side to achieve similar results. So by having more management, more controllability on the demand side and reducing it, we can consider it, or the term considers it as a resource similar to that of a conventional generation side resource. So conservation measures save energy by doing away with certain types of consumptions. For example, insulation of a house reduces heating, air conditioning needs over the life of the house. We can see here an example in the Saudi residential buildings through wall insulation, through reducing lights, infiltrations, and how much that can impact on the different regions of Saudi Arabia through a study by CAPSARC. The term demand-side management was used in the regulated environment to refer to the implementation of extensive programs that modify the demand of the system. As we saw, the energy efficiency programs, the energy conservation programs, renewable energy, and so on. Load management programs have the ability to switch loads on and off to effectuate lower demand in the system at various times, particularly at times of peak load. So some of the programs include the participation of some of the consumers through certain appliances that can be controlled through an aggregator that is in direct contact with the grid to reduce the peak by interrupting some of these devices in which the consumer has participated and agreed to do so to get some monetary return or some credit in their electricity bill. In practical terms, a demand-side management program is any measure that influences load on the consumer side of the meter. Okay, so demand-side management can happen through energy reduction programs, load management programs, in which we have the direct load control or the peak clipping under load leveling, valley filling, load shifting, and we'll look at this in the next slide. Then we have the load management program through tariff incentives, so time of use tariff, critical peak pricing, real-time pricing. Those can provide incentives to the consumers to indirectly shift their loads. And then we have the load growth conservation programs that we have talked about. So in analogy to supply side resources, the demand side resources can be targeted for base, intermediate, and peaking applications. We can see at the top left, the flexible load shape. As we mentioned, the loads that have slack time, that have flexibility in which we can shift their use. Then we have the peak clipping, so through energy efficiency, for instance, especially for those appliances that are used or equipment that are used in the peak time. Then we have strategic conservation. Again, if we change behavior, if we install insulations, for instance, can result in strategic conservation that reduces the load. The strategic load growth, on the other hand, to ensure that the load is growing strategically rather than being directly happening within the peak to make things harder. Then valley filling, which is again a great opportunity if it could happen, to direct the additional load towards the areas of off-peak, of low consumption, to improve the load factor profile. So to use the assets in a better utilization factor, then we have the load shifting if we have the ability to shift the load from on-peak to off-peak time. Here we can see some cases of demand-side management. In Germany, there is the permanent reduction of the demand side by the use of more efficient appliances like washing machines, refrigerators, water heaters. Again, those are equipment that have slack time. Infrastructure designed for peak demand situations. Of course, the infrastructure are usually designed to be able to cover the highest peak. The commercial consumers often charged based on their peak demand. Usually the commercial in countries like United States, some countries in Europe, not only charged for their energy cumulative use, but also for their power peaks, because the generation side have to provide that. So ratchet clause, among other techniques, can be used to incentivize, again, the consumers towards better load factors, better utilization of the assets, better distribution of the energy use. Shift of electrical demand from times of deficient or defects to times of surplus availability. Provide price incentives to cause load shifting by smart meters. And smart meters are obviously an important part of the system when we consider demand side management. Different price incentives like the time of use or seasonal pricing. Here we can see in the figures that the target is to direct the growth. We can see here in the right figure, the red part is the target to direct the new load to go towards rather than coming also on top of the peak in the green part. So we can use our existing assets and delay the need to add more capacity, meaning more power plants. Typical examples of demand-side management programs. There is a number of utilities that have already deployed or are considering the deployment of advanced metering infrastructure on a system-wide basis to enable price-sensitive demand responses. The number of advanced metering infrastructure units deployed in the United States exceeded 70 million and is growing year by year. Of course, also here in Saudi Arabia, there was a massive program to advanced metering installation. Of course, when we talk about advanced meters, there are several types. There are the types that help to record the consumption. And then there is the two-way communication in which the installation of local PV systems, for example, at residential, and then selling. So two-way communication, the local consumers or the distributed generation can be more of a dynamic part of the system that sells and buys, not only gets from the grid. So the intended load segments for base load are motors, water heaters, refrigerators, lighting. For intermediate load, we have the building weatherization in terms of how we design the system or the building, including the windows, doors, to enhance the consumption of lighting, of air conditioning, for instance. The air conditioners or heat pump efficiency improvement by applying a stricter efficiency standards, like what we have here in Saudi Arabia with the star labeling for appliances, and then time of use tariffs. For peaking, the air conditioner control, thermal storage, HVAC, high peaking rates. Okay, load management programs, there are the key focus is to strategically reduce customer use at peak load times. The deployment of these programs avoid the need to construct more peaking units, meaning more power plants. Such programs have typically minor impact on total energy consumption. It doesn't reduce the total energy consumption, but it helps to direct it towards times that are in which the assets, the existing assets, are not used. The two major classes of programs include the direct load control and the indirect load control, as we saw, the interruptible, curtailable, time of use rates, or the deployment of specially designed incentives for load management. So the steps start with energy users sign up to a voluntarily reduce energy use. Then electricity demand surges, for example, due to extreme weather. So the system indicates that there is a need to reduce the total consumption after a specific time, 1 hour, 30 minutes. Then the participating appliances can start being interrupted, in which the consumers have already participated in such program as the demand response program. Users reduce their energy consumption, whether automatically or manually. And when we talk about demand response, we're talking more of an automatic application of the curtailment. Reduced demand helps balance supply and demand and stability of the grid. Users are paid for their reduced demand. So that's the incentive, as we indicated earlier. Demand side management activities focus on the customer side of the meter and aim to influence the end use of electricity so as to bring about the desired changes in the utilities load shape, as we have seen the different shapes profiles. Demand side management in practice has become a collection of programs for increased efficiency, load management, and conservations. Those programs aim to reduce the need for more electrical energy generation. Load demand is not considered to be fixed. Changes in demand are planned concurrently with supply side operations. The execution of demand side management programs and energy dispatch is done in an integrated fashion. The dispatch of implemented demand side management programs become an inherent part of the system operations. So again, with increased renewable energy sources, more controllability over the demand side can become more needed in comparison to a system with conventional resources. So the impacts of demand side management include the modification of the chronological load shape, the reduction of the peak load, the delivery of electricity at a lower consumption level, reduction in the overall emissions, as we intend to avoid the ram up, which increases the emission deferral and possible avoidance of the need to construct new supply side resources. Okay, so let's look at the key challenges of the demand side management implementation. Electricity service providers need to overcome the disincentive caused by traditional rate market. In environment in which there is a wholesale profit-oriented companies generate electricity, sell them for transmission companies, again profit-oriented, and then the distribution companies or electricity service providers, which try basically to sell as much commodities as possible. So the more electricity sold, the higher the contributions to profits. The deployment or the development of rate structures that not only permit the recovery of demand side management program costs, but also provide other incentives to encourage demand side management implementation. And we'll see a numerical example of some of possible programs. And the education, training of customers through the timely provision of information on topics such as effective energy utilization, the important role of demand in meeting supply-demand balance, and the cost-effectiveness or the cost-effective approaches to manage the customer energy needs in a primary requirement, or is a primary requirement. Then we have the design of the appropriate tariffs and incentives for customers to improve the efficiency and adopt new conservation measures, shift loads to periods of lower demand, and obtain regulatory approvals. So looking into the shift of demand and dynamic pricing, we see an important factor, importance of optimized scheduling. Approximately 20% of the generation exists only to cover peak demand, which occurs at only 5% of the time. Let's break it down. So the peak demand is required for a certain amount of time. If we look at an annual basis demand or profile, then probably in a month or 2 months during summer in hot areas, winter in cold areas. So there is 20% of that system is only used for that peak demand, which can happen through even several hours per year. So the fact that demand shifting, or by applying demand shifting, we can reduce the need for that or portion of that infrastructure. Aim at optimally utilizing electrical system assets, privileges the flexibility that can be offered by households in the best possible way while maintaining their comfort at the same time. And we will look at this later on in the comparison of promise versus reality, because demand side management can be seen as a fix of a system problem more than a consumer problem, while the main factor or influential on the demand side management application is the consumer. Then dynamic pricing produces self-interested agents, which leads to electric consumers who seek to shift their consumption. So the idea here is how possible is it to incentivize the consumer to adopt these measurements. This scenario results in better balance in terms of demand and supply. Okay, advancing and postponing the switching points over the planning horizon facilitate altering the energy profile. In today's grid, the power plant ramps generation up or down following the load. So that's what we call load following. Power plants ramming is slow. It accelerates the devices wear and tear, drives to more emission, and the ramming rates of power plants are limited. Renewable energy sources are dependent on weather conditions, so it's not even possible with them to ram whenever it is needed. So dispatching loads is a trending approach to complement generation dispatch, and that's what we call generation following. So the idea is today with conventional power plants, we mostly are load following. We find what is the load, and then the generation follows it. With more renewable energy sources integrated to the grid, that becomes more challenging. So the demand side management helps towards a little improvement in being generation following. We follow the load because the load fuel, if we can call it, is not under our control. The solar radiation, the wind, and so on. So here is an example of the hourly load over the day, in which without the scheduling, this is actually flipped. Load without the scheduling is in the left, and with the scheduling is in the right. You can easily notice that the utilization factor, the load factor, is low in the left side. Why? Because sometimes we use little of our assets, and other times we use a lot of our assets exceeding 3.5 kilowatt hour. With scheduling, this becomes more of a stable load factor, in which the total or the peak is reduced to around 2 kilowatt hour by shifting some of the peak load into the off-peak load. This looks promising, this looks great, but it is challenging to implement. So we said some of the techniques are time of use tariffs. Where are they used? How are they implemented? Here we will see some examples and snapshot of some countries that apply time of use tariff, how they work, the benefits of their systems, the key enabling factors, and some examples. So the different types of tariff include the static time of use pricing, in which typically it is applied at some times. So between 3 and 4, this is the price. Between 4 and 5, this is the price. Basically on peak and off peak. It's a static pricing based on the on peak and off peak times. Then we have the real time pricing, in which it is a more dynamic system that updates the prices based on the current status of the load. Here we have variable peak pricing, which is basically a mix or a hybrid system between the dynamic pricing and the static pricing. Then we have the critical peak pricing, in which the rate of electricity prices increases substantially for few days in the year, which are the peak days. Okay, so let's look at an example in which we have an energy service company that undertakes a lighting program to implement energy efficiency through the replacement of 75-watt incandescent bulbs by 18-watt LEDs or fluorescent lamps. The life cycle is 10,000 hours, and they produce equivalent amount of the illumination. To make the program attractive to customers, the energy service company offers a $2 rebate on each installed compact fluorescent lamp. We have the marginal cost at 3 cents per kilowatt hour. The average cost of producing electricity is 2 cents per kilowatt hour. The number of compact fluorescent lamps installed is 1 million, and the administrative overhead costs are $1 per lamp. So here we can start computing the energy saving. We had each lamp consumes 75 watt, and it is reduced to 18 watt. Multiply that from power to move to energy by the life cycle, which is 10,000 hours, multiplied by 1 million, the number of the lamps. So that gives me 570 million kilowatt hour. Okay, so we have the cost. We said the marginal cost is 3 cents. We multiply that number by the marginal cost, then we get $17.1 million. So that's during the life cycle of this project. This is the energy saving gain. The program costs, we can deduct now the cost on the energy service company, which is, we said, $1 administrative cost, and then $2 as a rebate for each installed lamp. So $3 per lamp multiplied by the number of the lamp, we get 3 million. We deduct this from the 17.1 million, so we get 14.1 million profit. This profit can be divided between the consumer and the energy service company. Here we have a share of 15% for the energy service company, 85% for the customers. So we get 2.12 million for the energy service company and 11.99 million for the customers. The ability to directly capture a portion of the net savings provide incentives to the energy service company to undertake more widespread lighting programs. So if they want to check the cost, which is the $3 per lamp, divided by the energy savings, 570 kilowatt hour. So that gives us 0.52 cents. Is that less or more than the difference between the marginal cost they charge for the customer and the average cost, which is the cost of their generation of electricity? We said 2 cents and 3 cents. So basically, that's a program that makes sense to the company. The average cost plus the demand side cost plus 0.52 is less than the 3 cents, the marginal cost. So that's a profitable project for the company. The sole building code, also, since we are talking about the energy efficiency, dedicates a section about the importance or the mandate to install equipment that supports the sensors for lighting by means of any automatic control device required in sections shall either be manually or controlled to automatically turn the lighting on to not more than 50% power, except in the following spaces where fully automatic on is allowed. We have the public corridors, the restroom. So basically, these are the areas in which the coming in and out is more often. Areas where manual on is important for safety or security reasons, primary, building entrance, and lobby. The measurement of demand-side management cost effectiveness is difficult and is, to a large extent, highly policy dependent. Typically, demand-side management programs need to pass certain tests to be authorized by regulatory agencies before utilities can implement them. The cost effectiveness depends also on whose viewpoint evaluation is made. Is it based on the viewpoint of the participating customers, non-participating customer, utility stakeholders? Everyone will consider based on their requirements. There is controversy and uncertainty in the adoption of demand-side management programs in the areas of customer behavior prediction and the various assumptions used for particular programs. So basically, demand-side management, as I said earlier, depend heavily on the consumer behavior. So if no enough incentives or comfort level provided to consumers, then it will be hard to obtain the results that are desired from demand-side management. The savings due to demand-side management programs are difficult to determine accurately. For example, an owner whose home has been insulated may set his thermostat to higher temperatures, which eliminates some of the benefits. So basically, if we are comparing two similar houses, one is insulated, another is uninsulated, we will probably assume that the insulated house will consume less electricity for air conditioning, for example. But the behavior of the consumer might change that. So the person in the insulated house might set their thermostat to 20 Celsius degree of the air conditions, while the other in the non-insulated can set it to 24. So again, we are assuming based on the factors, but the characteristics of the way the consumers use their devices make the most important difference. Basic reasons: demand-side management has not lived up to its promise. It has done a poor job of solving the customers' energy problems. The key failures of demand-side management include the fact that it attempts to force standard solutions for each customer's unique energy problem. While it's the most important part of the success of the system, demand-side management is based primarily on supply-side economics rather than the customer's end-use energy conservation economics. So to conclude, we have gone through the demand-side management from different aspects: the customer benefits, the utility benefits, the social benefits. In the customer side, it helps to satisfy electricity demands, reduce and stabilize cost of electricity bills, maintain, improve productivity. From utility benefits, it helps to lower the cost of the service, improve the operating efficiency and flexibility, and improve customer service. From the social benefits, it helps to reduce the environmental degradation, the conservation of the resources, and protect the global environment. Here we come to the end of this workshop. I hope you find it helpful. I'll be glad to answer any questions you might have. You can contact me at a.akassem@iu.edu.sa. Thank you very much. That was my time with you, and see you in another workshop, inshallah. Assalamu alaikum wa rahmatullahi wa barakatuh.